Last time we had a look at the concept of inheritance, where you can write a class, build on some logic, add fields, and do all of that, and then have another class that inherits from that first class, and with it, all the logic you've defined in the first class and all the fields, everything that's in there is also in this second class you created, even if you don't write anything in it, just by virtue of it inheriting. As a counterpart, so to speak, to interfaces, where you define that something applies a contract to your class that enforces certain standards, certain properties, certain methods in terms of signatures. Only with the interface, you only get the signatures, and the interface doesn't care how you implement it. Whereas with a base class, with inheritance, you receive all the logic pre-built, and you don't have to define that yourself. Though you can. We have also looked at virtual and override, a way to redo the logic of the base class in case it doesn't apply to you specifically. We're gonna deepen our understanding of base classes a bit, and we're gonna mix in some interface logic again. Or, well, a similar logic to what was in interfaces, not interface logic directly. And we're gonna start by creating a base class, mount. Because maybe players don't want to walk everywhere. We want to have mounts, something that can speed up travel. And the mount should have health, of course. If they get hit, maybe you lose the mount, or you have to heal them first. Something like that. Private, and let's do that way. And public. Now, we're just gonna create a property for that, as always. So we can't just change the health, but we can read it. And we're also gonna have a speed, which we're not gonna store as a field. We're just gonna say returning a fixed value. Let's say 0. The default mount has no speed, cannot move. And public mount. When we create the default mount, health will start at 1. Right, so we have a basic mount. We can create, which will have some health, 1 health, and 0 speed. Now let's create an actual mount that we might want to use. Let's create classic, the horse. And the horse inherits from mount. Same logic as with interfaces. And in theory, we now have a horse. Is it? Okay, keyboard switched again. Horse. Like that. And that should take care of things. Yeah, that worked. We have a functioning horse and a functioning mount in general. And this horse will have all the properties of a mount. So we can sort of write a line. Let's do like this. Mount.health. Now let's make this a bit more fancy. Let's say mount age is that plus speed is plus mount dot each. We're gonna do the same for the horse. We run this, and so both are identical right now because we didn't override anything in horse, we didn't give it anything special. We should maybe start by giving our own version of speed. Public int speed get return. A horse will have a speed of 4. If we assume that a speed of 1 is the default speed we have as a player, maybe? Yeah, let's think of that. Standard walking pace would be 1, running would be 2, and a horse by default is twice that, so 4. Seems fair enough. Let's do that. So if I call the code now, we have a speed of 4 in here. Remember last time? There's a weird situation now because speed exists already. We have it defined in mount. But we now have a second definition here in horse. And what that means is that we create a horse as mount. Just store horse as a mount. Because it's the base class, it fulfills all the obligations a mount should have. Because it inherits all of that. Similar to interfaces again, just same principle, we can store a horse as a mount in general. And if we do that, we look at the horse as mount, we get a speed of 0 again. Just like with interfaces, or more specifically with explicit interface implementations, this speed right now is only visible if you look at it as a horse. If you look at this horse as just a mount, we will limit ourselves to this stuff in here. And this stuff already contains a full definition for speed. So we're going to use that. And that's why last time we introduced the idea of virtual. Only virtual alone is not enough. You can see speed 0. We said on this end just speed is virtual, which means we expect someone else to get a different definition for speed. When we look at horse as mount right here and check speed, the compiler will see, or the computer later during runtime will see that speed is virtual. So we should not limit ourselves to just this. At least for speed, we should leave this in as an option, as a fallback if we don't find anything better. But we should ask the object itself, the real object, which is a horse, do you have anything better that we should use? And we do have something more explicit directly in here, but we didn't tell the compiler, please use this over whatever you have. So it's gonna ignore that. We have to override it. We have to specifically tell the compiler, this method is to be used over whatever you have already. You have a virtual method, that means we expect to be just the default, and likely our child classes, the classes that inherit from us, will have their own implementation with something more specific. Check for that before you call this code. And the child class, horse in this case, does have something more specific, and we tell the compiler this is meant to be used over whatever you have already. So now when we call it, speed will be 4, the special implementation we've defined on horse. We can go a bit more interesting here. Let's say we have a special type of horse. Let's say a Pegasus. A horse that can also fly. Is it Pegasus or just a... Is Pegasus a classification now, or is it just the name? Well, whatever. Let's copy that. They will get an even higher speed, say 6. Whoop, that's not what I should press. And let's say this is a new Pegasus. Horse's mount is just a Pegasus now. If I call this, it will call 6, because this is the most specific implementation, and it specifically said, please override. Let's remove this override here. Now we drop to 4. Pegasus has a speed, but it did not classify this as it has priority. Override whatever behavior you have. But this is still virtual, so the compiler still tries to find something better than the default. And so we end on this thing in between, which is marked as override. We start the base class and see it's virtual, and then we go upwards to our actual class and try to find anything that's overriding the base behavior, which this one does. So for now we switch to this, and then we go to the next class further up, check, does this have anything to override? It doesn't. And then we would go further up and further up and further up until we hit the actual class we have. So the most specific override is what we use. Can also go the other way. Can drop the override here and just do it in here. Or can I? Could try this. Gives us a different error. I'm overriding something, but speed already exists. So am I overriding the speed? But the speed is not virtual. I can't override it. So what am I doing? Do I mark this as virtual now? That's interesting. I'm looking this as a horse. I'm looking at this Pegasus as a mount, sorry. And I do have an override in here, with a specific value. And it's still using this down here. Weird. So you can have some fun with overriding and virtuals. There are constellations in where you do mix these things a bit, especially with the new keyword, which hopefully we're not going to touch on the future because it is a strange way to deal with things. But in theory, you could use the new keyword in place of virtual override to also have a sort of meaning of override, but different from the override you know. And we're not going to touch that. I hope you don't ever use or have to use that. The most sane way to go about this is always you start with a virtual and then you override wherever you need it. If you don't override it, just don't include it at all. If you're not a base class, if you're inheriting something, either override that method or don't include it at all, don't just write it out. That's the best way to handle this. But yeah, so with this, we get different values depending on what real class we have. Let's drop the Pegasus. And that's all stuff we talked about already. So this was mostly recap. Let's also include a method in here, just for completion. Public. Think of a move method. Let's go for bool move. And this move method will be applied when your mount is moved somewhere. Let's say you have a system where you don't directly control your mount, but you just tell it where you want to go and it will do some path finding internally and move as best it can. It has a mind of its own, sort of. And it will return true or false depending on if it can move to somewhere where you designate the target or it can't. So by default, let's say it can't move. Which makes sense for a base speed of 0. Can't move anyway. Then down here, we want to make an implementation. Public bool move. Use that, and let's skip the formalities with the real code that happens in here and just say, yeah, I can move it, true, whatever. And just as before, we don't want to use the default behavior. We want to use our specific behavior. So we mark that as virtual on this one end, so the computer will look for a better implementation. We mark this as override to tell the computer this is a better implementation, or a more specific one at least. More specific, that's the correct terminology, I think. So now we have a horse. That's basically a mount with some slightly different behavior. Let's also change the health. Changing the health could be done in two ways. Let's say I want to offer the health, the constructor, let's say we have a horse. And when I create a horse, I want to set health to 10. So health is private, I can't access that directly, and I don't want to directly change health from horse because there's maybe some fundamental behavior with health that I don't want to accidentally interfere with. So we have two options. Option 1, which might be useful anyway. We can set health in the property. So we add a setter in here. And then we can, if value is less than 0, can do this. Set health to 0, and if it's not less than 0, we can just set health to whatever it is. So health cannot be negative. The classic. We don't want anyone to just set health. We don't want this to be possible. We have some other mechanisms for this or removing health. So we are going to protect this part. We don't make it private, so our child class horse can access it, no problem. But we don't make it public either, so only our child class can see it. We make it protected. We can see it. Can also set that in here that way. We ourselves can use that, or we can use the field directly. It doesn't really matter. I mean, in theory, you could argue that this is faster, more optimal, because we don't have to go through this code. But honestly, that's a level of micro optimization that's beyond ridiculous. But anyway, horse then can access the property. It can't see the field anymore, so we have to go through the property, but it has the access rights to the set method in the property, so we can change health for horse in here. Alternatively, we could say in health, we do it like this. We demand that we provide the health in the mount, in which case we would have to use the standard syntax for calling the base constructor. And I made a mistake. Right, I forgot to change this up here. That's better. So 1 health in here, because I specifically set 1 health. That also means I can do this now, so probably not a good idea. I should not be allowed to just define the health when I create this, so let's make this protected as well. Now I can create mount anymore. Well, in that case, maybe we just drop it. And this way, we prevented anyone from creating a mount. Is that an issue for us? I'd argue no. I'd argue that mount not being able to be created directly is a good thing. Because mount is just defining some base behavior for what a mount is. Similar to an interface, just we do have some code we want to rely on. Some logic, at least for health. Even if the rest is all just default stuff. Also important, we want to have fields. At least this health field that has to be there, which we couldn't guarantee with an interface. Interface can only guarantee the property, but not the code in the property and not the field that backs it up. So the base class makes sense. But mount itself is useless because it's just a generic definition for what a mount is. It's not intended to be a mount in of itself. It's not supposed to be usable. Horse is usable. That's intended that way. We rely on the base code. And we add our little changes to it that make up a horse. Compared to, let's add a second one. Another mount, another mount. Let's make it a ghost. Let's have some fun here. Ghost has 0 speed, has 1 health, very fragile, but ghosts don't move in the normal way. Ghost doesn't move, so it doesn't need a speed. It will just teleport. Let's do it that way. A horse moves normally and a ghost just teleports. So horse moves fast and the ghost just blinks to somewhere else. Now, ghost and horse have slightly different ways to look at how they work as a mount, but they are both real mounts. Mount itself is not a mount, it's just the base definition. And we ensured that nobody can create a horse by making the constructor protected. We could also make it private. You can make private constructors. Same result, we can't create it anymore. But if we were to make mount private, the base classes would also not be able to call the constructor anymore. So this could not work. And without access to this constructor, we would not be allowed to use mount as a base class because we cannot initialize the fields we get. We might not see the fields, but we have them, and it's important that we initialize everything correctly. We need to call a constructor. Any constructor that mount has to offer. And the only constructor we have is private. So we need to make it protected so that horse and ghost can see it. Now we have the interesting situation that mount itself cannot be used. And our horse and our ghost both have their own definition for move and speed. We could argue that for the ghosts, since they have 0 speed, we don't need to override and can use the default behavior. Sure, we could save ourselves some code here, but maybe I do want to keep it in just to make sure that I don't rely on some default value. Maybe I later on change the default to just be 1, or maybe just to make clear that nobody can use it, I make it -1. And if I don't have anything in here, because I was too lazy, I might accidentally change the definition for ghosts as well. That's not a good idea. I might prefer the option to force us to implement speed properly, even if I don't use a different value. That sounds like a good idea, doesn't it? Similar to an interface, force the child classes to make their own implementation of something. We want both to have a move and a speed. A move method and a speed property. And they both should supply their own logic. We want to act as an interface in this case. We want them to force this signature, the get speed integer, and a move method returning a bool. We want to force those signatures like an interface, but we are a base class. We can only mark something as virtual, so we give a hint that something else should be preferred, but we still have to provide this default code here. I'm mentioning this because, of course, there's a way around this. We can force someone to implement something for us. And the trick is another keyword. If we leave out the keyword, it is just a method that's inherited by the base classes and everyone uses this code. If we mark it as virtual, that means this is functionally correct. Anyone can use this method. As in, we can call this method and the base classes inherently have that code. But we also marked it as virtual to mean you might want to use something on your own. It's probably better if you make your own implementation. It's more just a suggestion. And we can agree to that and say, yeah, we override it, let's do that. But it's optional. There's another keyword we can use. Abstract. Abstract is a keyword that marks this method as you have to make your own implementation. Because it forces the child classes to make their own implementation, we don't have to offer anything ourselves. So this might as well be written in an interface. Same logic. You have the return value, the name, the parameters, in which case right now it's none, so empty brackets, and a semicolon in the end to show that it's done. So this is how it would look like in an interface, but we are in a class now. We have some more restrictions. The first one being we have to mark it as abstract. So this is required. You have to use the keyword abstract. Otherwise, the compiler will complain that you're lacking any implementation code. And also, we want this method to be publicly visible, because the visibility is inherited. If we say this move method is public, it means it will be public for all the different child classes. If I make this public here, I am not allowed to make this private in here, for example. But I could, other than with interfaces, I could make this protected in here, which means I can see it and my child classes can see it. And in that case, I'm allowed to make this protected in here as well. That's regardless of the abstract, by the way. This is just a general feature of visibility. Visibility still applies and can be inherited as well. Now, this is an abstract method. It's a method where we define simply the signature and visibility. And that means that every class that inherits from us does get all the rest of the code. They do get the field, they do get this property with all the code, and they get this property. Everything is in there, except the move method. They do have to add their own code. They are forced to override move. You cannot opt out of this. Can compile? I can compile? What have I done? Wait, 990? I am confused. What have I missed? Oh. Okay, that was obvious. The constructor should have been for ghost, not horse, of course. So, and... Right, shit. Didn't want you to see that yet. Well, too late. You saw it. Ignore for a moment. Yeah, see, in theory, this is not correct. I can compile this, and this is correct. I can compile this. Horse and Ghost are now fulfilling their obligations. If I were to leave that out, if I don't override move, that would be an error, because then I have a move method without an implementation, because there is no default up here. Now, you've seen the message already, unfortunately, because I didn't pay attention to that. So, yeah. There's a downside to making a method abstract. And that is that because we don't have code for this method, this is now an illegal object, so to speak. I have an object which has a method, but there's no code to execute when I call this method. And so I'm not allowed to use mount as an object anymore. I'm not allowed to create a mount. We'll make this public. Try to do that again. Mount equals new mount. If I were to do this, I would create a mount, which in theory has a move method. But this method call goes nowhere. There is nothing here to call. That would be an error. So I am not allowed to create this object mount because I cannot create a functional mount. It is not possible anymore. There's something missing. And to make sure that everyone knows that mount cannot be created, should not be created, that it's invalid, that it's incomplete, we mark the entire class as abstract. As soon as if anything abstract in a class, the class itself has to be abstract as well. You don't have to do that. We could have just the virtual method again, which move, and let's keep it on one line like this. I can have the move method exist and be just virtual and still make the class abstract. That's not an issue. You can always make a class abstract no matter if it actually needs to be abstract or not. But the moment you have anything abstract inside the class itself has to be abstract as well. Because you cannot use the object anymore. And that was the error we got earlier. Non-abstract class, abstract, but it's declared a non-abstract class. Since mount is now abstract, I can just use it to inherit from in horse and ghost, but I can create it. If I try to make a mount, new mount. Might I have changed the constructor to public earlier? In theory, this looks correct, but it's abstract. So even if there's a constructor, I'm not allowed to use it. And so might as well keep it protected, since why should someone be able to see the constructor? Like, keep everything consistent. The class is not supposed to be created, so we hide the constructor, and we also make it abstract, since there are things in here we don't need to provide any defaults for. Any class should make their own version. We could do the same for speed, for the property. Make speed abstract, and we do it the same way we would do it in a interface. Just with the method, just like with the method. This could be an interface. This is now an abstract property in a class. And we override everything, and everything works just fine. If I don't override, we get an error. If we leave it out altogether, we get an error. So by making the method or property, which in itself is also just a method again, if we make that abstract, we force our child classes to override the behavior for this specific thing, while still offering other things predefined. We have already a field health. Horse and ghost will have that field, and we have logic in here to change that health, which both ghost and horse will have access to just by calling it. They don't need to define this by themselves, which they would need to do if mount was an interface instead of a class. So it's always a bit of a give and take. Inheritance provides certain features that interfaces don't have, but sometimes you don't need those features. So you might prefer an interface because it has some more flexibility. It's a bit simpler. And sometimes you want to have both combined. You want certain things to be not set by default. You want different classes to implement that in their own specific way. There is no default you could just apply without having some issues later on. But there's also code you want to just share because it's always going to be the same. So in those cases where you have sort of a slight mix between class and interface, you make an abstract class. You define code, you define signatures, and the child classes get the benefit of some inherited code they can use, but still have the option or are forced to provide their own definition for certain things that you want to rely on. Inheritance has one big downside. You might think that if an abstract class can do everything an interface can, I mean, we can define just signatures, there's no reason we have to provide this. We could just drop that as well. Now we have essentially an interface. An abstract speed property and an abstract move method. Well, this could be an interface as well. With this, we get the requirement for a class. But without it, we effectively have an interface. So if an abstract class can mimic the behavior of an interface, why have interfaces at all? Why would you ever need an interface if you could use a class that has the easy option to add some code later on? Whereas an interface, well, you're locked into everything has to be manually inserted as new code. As a new code? As new code. The problem comes when, let's say, we make a new enemy class. And let's keep things a bit simpler and let's copy this stuff over here. Same logic as with mount. We have health in an enemy, and maybe we have like strength. Return one, whatever, and public void tag. Yeah, also let's keep out the logic here. Too lazy to write something out. Doesn't matter anyway. We have now an enemy class. And maybe Ghost is special in that it's a mount, but to get a ghost mount, you have to first fight a ghost. So ghosts can be enemies too. So we do it just like we did with an interface. We have the base class mount because ghost is a mount, and we have the base class enemy because ghosts are enemies. Unfortunately, can't do that. Interfaces, you can have as many as you want. You can implement any number of interfaces you want, no problem whatsoever. But you can only inherit from one singular class. You can have multiple classes that inherit from the same base class, that's not an issue. If you go down the entire route from mount, you can split off into horse and ghost, and those can split off in others. You have a whole ancestry, basically. A whole family tree that goes up to one singular root class mount. But every class can only have one base class, one origin, one singular class you inherit from. You can't combine multiple. You can have a base class and interfaces. That would be possible. If enemy was an interface, then this would not be an issue. But as soon as you have two different classes, that's a problem. And in theory, there are ways you could make the language work with multiple base classes, but having multiple base classes causes a bunch of issues, and many of which I'm not even aware of because they are so ingrained in the deeper regions of the language. But we can find some simple issues already. We have mount, which offers a health through a field and a property, and we have enemy. Well, right now the code is the same, so you might think, well, what's the issue? It's the same code, let's just use that. Okay. What if the behavior is different? What if enemy allows negative health? You have now one field health and two different properties that behave differently depending on which one you would use. So which one do you use? In this field, is it the same field, or do we now keep separate health bars depending on if we have an enemy or a mount? Well, a ghost is an enemy and a mount at the same time, so which health has priority? Which healths do we use? Do we use both of them, or do we use just one of them? Can we use both? Do we do that the same way we do it with interfaces, with explicit interface implementations? Where you have to cast your ghost as an enemy or a mount to have access to health? So you have different health values? Or maybe does it only apply to the properties and the field is the exact same in memory? Like, that's a very simple conflict, which can happen with interfaces to some degree. That's where we have explicit interface implementations, but with interfaces, it's only about the methods to access something. And interfaces are already very specific. If you care about something as an interface, well, you already know you need to cast it as an interface anyway. But if it's the object in of itself, if it's just inheritance, you probably want to use the ghost as a ghost, not just as a generic mount or enemy. So having to constantly cast it as mount or enemy to get access to certain features that are offered in one or the other base class, that's meh. Also, if I have speed, I override speed in here. Well, do I override speed from mount? Or do I override speed from enemy? Again, do I have now two implementations I need to separately handle? Like override mount.speed maybe? It's just, you can always find ways to clear up any conflicts through syntax, like make concessions here and there and make it work in the end. It's possible. But I don't think there's, at least right now, a nice looking way to potentially handle this. There might be in the future. like, who knows? In a few years, someone might look at this and think it's the basic default feature of C#. What are you talking about? Right now, it's not. And again, there are tons of issues I'm probably not even seeing right now with type safety and whatnot. Base classes are just not allowed. Interfaces are okay because the number of conflicts are minimized. If two interfaces define the same signature and you implement the signature, the interfaces don't care what you implement. They only care that the signature is there. It doesn't matter for which interface you designed the code. They both have no preference for the code. With a class, you get finished code already and you now have to decide which one do you use. The only potential conflict with interfaces is with explicit interface implementation, where if you do care about the difference between interfaces, you have to write the code twice and mark for which interface which method. And then you do have to cast the object as a specific interface to get access to those methods. But that's not very common, and it's the only type of conflict you can get. And it's for interfaces which are already very much, we don't care about the specific object, we care about it in this specific context only right now. So there's a way to solve the conflict for interfaces, the only real big conflict. So multiple interface implementations, not an issue. Way more conflicts you get when having multiple base classes with very weird I can't think of the word. Very weird. What's the term? Consequences. I think that was the word I was looking for. So this, not possible. The easiest way to handle this would be to have two different ghost classes, one specifically as a mount and one specifically as an enemy, and then maybe make a method in here, like, let's do that right now, ghost mount, so mount, and then could have, ghost mount and ghost enemy. Like that, and then you could have public ghost. Oh, let's do it the other way. If I fight a ghost and I win, then I have the option to turn that ghost into a mount. And maybe for that I can provide the defeated enemy as a construct. There's a parameter in the constructor for ghost mount, and then we can set help to enemy.help, right? And take over the stats from there. To some degree, at least. That's the easiest way to handle it, just don't have any conflicts. Or you could turn mount or enemy or both into interfaces. Or you have an entirely different structure. So there's always a bit of back and forth and how do you arrange everything. That's designing your code, that's software development. That's how defining the architecture of your code. What is a class? What is an interface? Or not in the sense, what are they conceptually? Which data do you want to store as a class? Which data do you want to define through interfaces? Do you use abstract classes? What is the level of inheritance? Where can you combine things? Where does it make sense to split them up? Do they have shared code? How do I share that code? Those are all things you have to keep in mind when creating large programs. For smaller things, it's usually not really all that complicated. But if you write a large library, this can matter a lot. You have to think about what's possible, what's the most convenient way to use my library, what's the likely way someone is going to use my library. Those are then all things you have to consider. And because I haven't mentioned that before, one last thing for inheritance, for now at least. inheritance has another big flaw. Well, not flaw, but another thing that might put a wrench in your project. This is a struct, a generic struct for an effect, just a one-off. Yes, maybe a visual effect, or maybe it's tied to something more like spell, public. Spell is a specific effect. This doesn't work. Inheritance is exclusive to reference types, to classes. Actually, we don't care about the fields. This doesn't work. Structs cannot inherit. A struct is defined as this one thing and this one thing only. This stuff in here and only this. You can have interfaces. That's not an issue. Again, interfaces are the special thing where they don't qualify as code. They're just a way for the compiler to make sure that everything is agreeing on something. But it's not really sharing any code. It's not giving anyone anything and say, you have to use this. There are no conflicts on that level. A struct is a specific piece of data, and only this piece of data that you can store wherever, on the stack, on the heap. Everything you need to know about a struct is in this struct. Even if you have an interface, it is not providing you any code. Everything has to be implemented in this struct, so everything you need for the struct is in this one struct. If you know it's a spell, you have everything you need in between these two brackets. Guaranteed. With a class, you always have the option that maybe it's not everything in here. And you also need to include this other thing. Now, again, I can see ways to make structs work with inheritance, no problem. But again, there will be complications that I'm not thinking of. Especially once we talk about something like an abstract struct, that would be very weird, that doesn't make sense. But yeah, it's not possible in C# currently to inherit structs. Like, you could think at least inheriting a struct from a struct should be possible, but it's not. It's just one of those things you have to accept. Even if you can think of reasons why that's dumb and you can make it work just easily, if it was that easy, it would have been in the language already. There are probably really weird edge cases that you aren't even aware of that would make this a nightmare in the back end. And I assume it's one of those features that either too complicated to be worth it, because someone decided there are better ways to make this possible instead of struct inheritance, or maybe they are already working on it and it's just complicated and they need to take their time. So same with multiple inheritance for classes. Maybe they are working on it and they just haven't figured out a good way, or they're not sure it will be reliable enough. Who knows? That's for you to find out if you ever get to a point where you join the .NET team and the implementation there. So yeah. That's everything I wanted to talk about today about inheritance and abstract. That's the big thing, abstract. Class can be made abstract, which just means this class cannot be instantiated. It's just an abstract idea. This is how we imagine a class to look like, but it's not something you can actually use. Enemy cannot be made. There are no enemies. You have no enemies. Doesn't exist. Just the idea maybe. And you can apply that idea to something else, which might inherit some code and maybe some abstract definitions where it just assumes you make your own stuff up. You have a class that you can create that has some interface properties. Or you can look at it the other way and say you have an interface with the option to provide some code yourself. So newer language versions of C# interfaces can offer their own code directly, though still not any fields. So at least with newer language versions, you can get around some issues you would have with abstract class because of multiple inheritance. Which is again another point for you can make multiple base classes work, because interfaces can now have code and we can get around those issues. But yeah, it's all relative. Not everything is as easy as it looks first time. Now, since we have closed this part, there's still one thing that's loosely attached to inheritance. Very loosely. That's gonna be my segue. So we're gonna start with, let's make moving a bit more interesting. When I move somewhere, I move differently depending on what the environment is like. Like the horse, normal horse can't fly. And it probably can transport you safely through the ocean. So, depending on the environment, it can move better or worse or not at all. The terrain is important for movement. Maybe the ghost can basically move everywhere because it's teleporting, but maybe there are some special areas where the ghost gets blocked because it's not corporeal or whatever. Maybe you can't enter sacred places, something like that. So we want to include some way to limit the way we move. You can say, hey, string. The move method now includes a string for the terrain. And if I move somewhere, horse.move, I apply to, it's just moving on grass. And then in the horse itself, string terrain, I can say if terrain is grass, then do this. Else if terrain equals water, do this other thing. Depending on where I'm moving to, what environment I'm moving in, the move will behave differently. But if I just provide it through the string, while it is pretty clear what I'm doing, as a programmer I can see this and understand it quite easily, it makes it very easy for us to unintentionally have weird behavior. Like, I make just a typo in here. I miss one S. And now neither this nor this code will get executed, and we have something completely different. And maybe I do have some default behavior for this case. But then, despite moving in grass, my horse will do something weird, because it's using the default behavior and not the specific grass behavior. Just because of a typo. And now imagine that you don't have to just put that in one place, you have to put something like this in many, many different places. For different terrain, for different levels, whatever you have. There's a good chance that you make at least one typo somewhere. Ideally, we don't want to have typos mess up everything. Or at least if there's a typo, we want the system to warn us about it. Tell us we made a typo, this is not correct. Whereas with a single S is not valid. Well, something we can do. Public plus terrain. Let's do it like this. And then we have, let's keep it simple, public string type. And then public terrain string type type equals type, like that. And now I could do terrain grass equals new terrain. We call it grass. Can start with this. It's grass, and then we could do grass.type if we want to get the string from that. If I mistype grass, well, the compiler will tell me because grass with a single s doesn't exist. Two s, oh, you mean this. And that's defined once as grass. But maybe I don't even go for the type and just go for terrain directly. Might be easier. I'm gonna change the type in here. Change it to terrain. Like this. And now we can compare the type directly to this. So I have the string written once in here in our move method where it's evaluated, and once up here where I define it. So only two places in my code left. Minimizes the chance for a mistake. But my code might get a lot bigger, and right now I have grass defined in here, but I will have other methods where I call move method. And there I need to define grass as well, create a new terrain with this string, and so we're back at square one. Plus, even this has the option that I might make a mistake somewhere. And the move method needs to be implemented for ghost and other types as well, so still not ideal. Let's standardize this string. We have a class now, let's just use this class. Public const, we'll make a constant string. Grass. Grass. We create a constant. Just like we can create a constant for integer values, we can create a constant for a string as well, even if it's a reference type. Strings are special. And now we can do terrain.grass. And down here we can do the same. Terrain.grass. Alright. Looks a bit better. Let's make a second one. Water, water. And down here we can compare it to terrain.water. Let's minimize this. And now the string only exists once. It's still pretty clear what it is. It's visible, we can read it. But everywhere else we write compiler ensured code. Words. When we write water in here, or grass, the compiler makes sure that, oh, we have grass and water. These are constants. If I type this wrongly, the compiler doesn't know what it is, and we get an error, and oh, yeah, I mean grass with two s. Sorry. So we can reference that wherever we want. We have guarantee that it is the correct type name. It's grass or water. And we can easily compare that everywhere. Okay, that's nice. At this point, why bother with the type here anymore? I mean, at this point we might as well go back to just using a string. Right? Just use a string and then compare the string again. Go full circle, just this time the string is confined to a constant. All the advantages from before, plus the additional advantage of the compiler checks what we do. Okay, that means we don't need this anymore. Makes the object a bit smaller. There is no object now. We can create a terrain, but it's useless on its own. We only care about the constants. By the way, we can't prevent this from... We could, yeah, for example, we could make this abstract. That's one way to handle this. There's another way, but we don't talk about that today. It's not important anyway. But yeah, this way we could prevent it from being created. We still have the constants we can access. I'm gonna leave that out just to keep the type a bit simpler. But there are still downsides to this. If I call move, I could rely on these predefined constants, these strings that already exist. But maybe I don't know about these. Maybe I'm a programmer that just found the move method and decides, okay, I need to move somewhere, and rocky terrain, I don't know, just write a string in there. Or maybe I don't know what to write in here, just use null. Don't have a terrain. So it's very likely that by accident or intentionally we end up with something that's not quite right down here. Because we can call this with whatever. We have only a very limited number of valid values that would be accepted for move. But the move method up here allows everything. How do you go around this issue? We could go back to before, where terrain was a type that we passed on. Right? But then we have to store a string eternally and compare that string, and that's not quite right. There's an easier way though. Instead of storing a string with the type and then comparing that, we can do this. Can create a field, a static field that stores a terrain, an instance of this class. And store a second one for water. I mean, there's no limit how many static fields we have. And if we require terrain, well, we can create a new terrain still. But we know how to prevent that. We can just make a private terrain. That's what we did earlier for mount. We make the constructor hidden. In this case, we don't have any child classes we care about, so we can make it private and total. And suddenly, this is not possible anymore. The only way to get a terrain is by terrain.grass or terrain.water. The obvious issue you might see is that these are just empty fields and we never fill them with a terrain. We never create a new terrain to put in here. There are two major ways we can do that. We haven't discussed the whole initialization of objects yet. That's something we have to do in the future. But for now, it's enough to think that just as we did with the constants, we can provide a value directly in here. If you have a static field, or normal field, whatever field you have, any field you have defined, you can provide a value for, just like with constants. And we can, of course, pre-fill it with a new terrain. And in this case, even though we prevented terrain from being constructed outside of this class because it's private, in between these two brackets, terrain, the constructor for terrain, is visible. So we can call the constructor in here. We just can't call it outside here. Now this is one way to do it. There's another, but let's talk about that stuff once we talk about the initialization. That's a larger topic. I want to go over the order in which things happen and how static goes into this and lazy initialization and all that. For now, let's keep it simple. Let's keep it like this. Not my preferred method, by the way, because of reasons we can explain once we talk about it. I'm teasing it too much. Oh, sorry, I hear something. I did close. Okay, it's starting to rain. Just was thinking, but I closed the windows, so it's fine. Alright, so, yeah, not my preferred method for reasons, but this works. This has actually a name, this way of handling things. That's not what I wanted to show, but it's probably quite useful to see anyway already. We call this singletons. Because even though terrain is a class that we can create objects of, it's not abstract, you can create terrains. We made it so that the only one that can create a terrain is terrain itself. And terrain itself refuses to create any terrains except for these specific ones. Well, actually, this would not be called singletons. This would be a singleton. The name comes from the fact that there's only one single terrain in existence. No one can create terrain except for the class terrain itself, and it's doing so only once for the static field that cannot be changed anymore. So terrain.instance is the only instance of a terrain in the entire program. That's why that's called singleton. What we have here is not a singleton anymore because it's not the single terrain that exists. We can have many, many different terrains. Say we have some muddy terrain. Whoop. Okay, everything's good. But the idea is similar. There are a limited number of instances of terrain and they're all visible publicly. And now I can pass on terrain.water. Sure. Was that a flash? Oh yeah, that was a flash. That was a big one. Okay, thunderstorm's coming up. And I should probably wrap up soon because I'm afraid the thunderstorm is going to give me a blackout. Okay, if I'm suddenly gone, it's because I have a blackout, so just a warning. Not that it happens often, but I'm always worried about the option. I have a power supply for that. UPS here, but I plugged it out earlier because it's so loud. Should probably plug that in later if I'm done with the stream. Yeah, so we can get a terrain, and we can compare the terrain directly to the existing types we get from the static fields up here. Well, this is a very convenient way to handle it. We can pass on a terrain. The only way someone can give a value to move is by giving him some terrain that's derived from this class. That's the only place we can get terrains from. So we know whoever uses move will have to use terrain, will have to understand that this class exists and has these fields. So that's a safety precaution. And we can show that in here, when we get a terrain, it will be a valid terrain. We know it can't be null, because no one would implement null in here, right? That's a different topic. Well, okay, so we should have probably some option here for when it's null. And that option might be to just throw an exception. Do you remember exceptions? We talked about them. Terrain is null. Ooh. I should probably not do that in here, but make sure that it's up there. If terrain is null, then terrain is null. And since we're talking about inheritance more today, exception can be inherited from. You can inherit from an exception. So instead of throwing new exception, we can actually throw something more specific that inherits from exception, which will still be an exception. You can still cast it into exception just fine, because it's the base class. So we can throw it, but it's more specific. Like this. It's called the argument null exception. It's one of many different existing exceptions in the code, and we can use this instead of just a plain exception. So just looking at the type of exception that is thrown, we already can infer what is happening. which is very useful. We don't have to rely on the message making sense. We don't even have to have a message. I mean, argument null exception, there's only one argument, so okay, we know what happened. Even without looking at the code. And I mean, once you look at the code, you see that the only way we can throw it is in this condition. But even without the code, without knowing anything, by looking at the type of exception that is returned, you can see, okay, move had an argument null exception. The argument, terrain, the only argument, must have been null. So it's useful to, instead of just throwing an exception, throwing something specific, which itself will inherit from exception. Well, specifically, this will inherit from argument exception, which then inherits from exception, but inheritance, that's how that works. But yeah, so it can be null. That's something we have to be careful about. But any other scenario, terrain will be one of the predefined things in here. Nothing else is possible. So that's good. Plus in your language version, you can make sure that it's not null and make the compiler enforce it. So then doubly sure. Only downside here is that, well, this is a bit to write out. That's a bit annoying to write. That's don't like that. I have to make the constructor specifically private. I have to write that out. And I have to add all this text just because I want to have grass, water, and mud. Don't like that. So, what can we do? With our knowledge so far, this is pretty optimal already. And just to be clear, this is an interesting solution. It's a good solution depending on your circumstances. This can bring other benefits, right? Just to be clear about that. Just for this specific situation, there's a better solution. See, instead of doing all of this, let's just copy it to have a comparison. How about we get rid of this? And can I make multiple selection? Yes, I can. And let's get rid of this. And actually, since it's always the same, also of this. And of this. Let's just keep it for just the names. Let's put some commas in between so we know it's different entries. Don't forget the curly brackets. This is much shorter, much simpler, right? Only this is of course not valid code anymore. That's not a class. This is nonsense. So calling it a class doesn't work. We can call it something else though. Enum. Enumeration. As a list of things, which is why we use commas, because we just separate them as a list of things. And we usually spread them out into individual lines, makes it easier to read. Enums are a way to do this. The same thing we did before. Effectively, these are now fields or constants. Well, constants is more closer to what is actually inside a class. That's the equivalent. A class with some constant fields named grass, water, and mud. And that's what we pass on to post.move. But the type of those constants is the class itself where the constants are written in. So it's more like the static read-only terrains we had earlier. What we pass on is a terrain, but the value of this terrain is a constant that's defined in here. And an enum is inherently a value type now. It's not a field we store in the static part of memory with a reference to somewhere of an actual object on the heap, which needs to be instantiated when we run our program. No, this is just a constant that exists, and we simply limit ourselves to this is a type now. And we can compare that like any value. What's more, enums are relevant to inheritance because they themselves are not their own thing. They inherit from something. And this is where I have to break some understanding we established earlier. I said structs cannot inherit from other structs. And that's true. That remains true. Enums are not a struct, but they're still a value type. So they're in the same ballpark. And they inherit from a struct, from another value type. Let me demonstrate something. Int I equals terrain.water. Now this doesn't work because terrain is not an integer, but I can cast it, no problem. And terrain t equals 2. Doesn't work because 2 is an integer, not a terrain, but I can cast it just fine. Probably have some. Let's clear some code. Actually, let's drop this code. Let's focus on just the enum right now. And drop this. Console.write line. And let's just output I like that. And no, let's do it this way. I think we got 2, and then we go for t like this. Go run this code. You get an output of 2. The 2 can be converted into terrain, and we can convert it back to an integer and output it. As I said, terrain as an enum inherits from something. Any enum you have, they always inherit from a struct. And the default they inherit from is int. You recognize this pattern? Only integer is, of course, the int 32. And integer is a value type. So enum is a value type that inherits from another value type. Sort of. It's not strictly speaking inheritance, but it uses this syntax and it's kind of inheriting the properties in that it's right now a 32-bit signed integer value. That's what enums are in the background. It's basically, we have a bunch of constants, yeah, but the constants we store are integer values. So this is just fine. It doesn't have to be integer though. That's just the default if we don't specify anything. We can specify other types to inherit from, sort of, like uint, which is fine. We can store an unsigned 32-bit integer if we store in terrain. Terrain is now an unsigned 32-bit integer, or an unsigned 8-bit integer. Still works. If I go for 256, we get a little issue because terrain is limited to 255 at most. That's a byte. We go for int again. Or let's not use int, let's maybe go 1 up short. Then it works. We go for minus. Doesn't work anymore because casting is... That's better. So depending on what we do, we can inherit from, sort of inherit from other types. Unsigned short doesn't work because it's negative. Short did work. Let's go for int, or let's maybe go for long this time. also works. So all the 4 basic integer types work in their signed and unsigned version. And if we look at the value directly, if we go for rain.grass, for example, let's drop this above. You can see the standard value would be 0 for grass, water, that was a typo, uppercase, water is 1 and mud is 2. That's the default. It just starts counting from the first to the last, 1, 2, 3, etc. You can change that. Let's say grass is -1, water is maybe not that big, and mud is 0. So now mud is 0. Water is whatever that is. And grass has this number. So you can assign specific values if that's important for you. And that might be important because we do some math maybe with it. That might be relevant. But you can also leave that out, which is what you're going to use this the most of, I assume. And for the most part, you would use it like this. You only specify that if you have very specific needs or if you want to make sure that certain values stay in place, which has other reasons that we can talk about some very, very much later time. But this is an enum, and again, it's loosely connected to inheritance because it kind of breaks the weird rules. It is a value type that sort of, kind of inherits from other value types. So that's a fun thing to do. And it's very useful because it limits use to some named, as far as the compiler is concerned, enforced names, values that you can easily share in your program, especially if you have a small piece of data. You can use a byte. Again, it's a sort of micro-optimization, and most of the time it's not really limiting itself to just 8-bit. That's usually relevant when you have large data packages and you serialize it or something, then it could be interesting. Just leave it out. On the most parts, 32-bit is perfectly safe to use. You don't get any benefit from making this smaller, most of the time. But you have this just the small integer you pass around as a value, and you can compare it and check things, and it's just really useful for stuff like this. And before I close, one last big mindfuck. You might remember this. Integers have a built-in method. Integers are predefined types, int32 in this case, for int, and they provide certain methods that you just always have, like toString. If you remember that, everything has a toString method. Now we can finally talk about the reason why everything has this toString method. And that should have given you the clue. Everything has toString because it is a method defined in the base class that everything uses. And this is another case where we kind of break the rules a bit. But every single type we have in C#, doesn't matter if it's a predefined type or a type you create, everything by default, automatically, you can't prevent it, inherits from one singular root type. Our horse might inherit from mount, but mount itself inherits from this other root type. And so does integer so does long, and so does every enum we have. Even your structs. Another case where structs, even though they can't inherit. Well, this is another special scenario. It's very special type. And this one special type that everything, even structs, inherit from. It's called object. As you can see, it's lowercase. It's another special type, one of the primitives. It's the fundamental type of everything. Everything is an object, even if you can't see it. Even if it's not explicitly stated, you don't have to. Object exists everywhere, and you can instantiate it. You can create a new object like this. Perfectly valid. It's normal code. It's just an empty object. It doesn't do anything. There's no data to store in there. But it exists. It's there. It will just mean you reserve an address on the heap somewhere. There's nothing in there. It's just a singular address reserve. Doesn't really take up any space, really, except for the space that's absolutely needed to mark this as there's an object here. But exists. And object, the class object, defines four important, well, more or less, let's say important methods. Four different methods that all exist in object. They're all defined in there, all written in there, and every single type inherits from object, so every single type, doesn't matter if it's a value type or reference type, will have access to those four methods. And that's why int has a toString method. It's one of those four methods defined in object. And it's one of those special situations. Object is very, very special, so you don't override. I mean, you do override, but for structs at least, it's a bit weird to think about how you have a class object that a struct inherits from, but it's one of the few exceptions where some magic in the background works specifically for the inheritance for object. That's an exception that specifically code is implemented, so you don't have to worry about a general case of we have a struct that something inherits from. They can deal with that because the cases where it's important, there is specific logic in the framework, in the background, in the language to deal with inheritance from object. Very special case with very special exceptional handling in the language. That's not applicable to any type in general. It's only to objects specifically. So that's why you can have this weird situation. Now also means we can have this. I can store my integer a in this object O. What happens now is a is a value type, O is a reference type. We store something in a. That's something we talked about with the interfaces already, when we had a struct stored in an interface variable. That's the concept of boxing. Essentially, here we say we store the value in this reference type. It just means store a, copy it on the heap, even though it's right now on the stack, inside the method, the stack frame for main. Make a copy of it on the heap as an integer on the heap, and then use that reference, that address, in this O. So we're boxing it. We're not storing it directly in O, we're storing in O just an address for a place on the heap where we copied this value from the stack. That's where you can have structs and objects as well. Same as with interfaces, it's boxing. By the way, at least in older versions, this, even though it doesn't do anything, has its uses for a specific scenario. Object in general can be very useful, but also having an empty object like this can be useful in certain situations, though for the newer language versions there are alternative ways to handle that situation, but it's still popular. So this is not useless, though I only know of one singular use case. Yeah, and with that, I think we have enough of a mindfuck. That's all we have to discuss for inheritance for now. We have abstract classes, and I demonstrated enums, which, I mean, they're loosely connected, because they break the inheritance rules a bit, and they're useful just in general. I just wanted to complete the 4 basic types, sort of. We had classes, we had first structs, then we had classes as reference type, then we had the concept of interfaces, and now you know enums. And those are the 4 different types. There are some newer types, quote-unquote types, in the newer versions, but they're only extensions of existing ones. I mean, enum is also just an extension, sort of. If we break it down, we really have a value type with struct, reference type with class, and interface as a third thing that's not any data and just a contract. I digress. Anyway, that's enough for today, and this is probably the last time you see the one compiler, because I'm getting slightly sick of it. So next time we're gonna start working inside proper IDE. And I'm gonna leave you with that. Have a lovely Sunday. Till next time.